Hello, this is Emma. I would like to explain about thought that fundamental to know in order to study aerodynamics. This video is titled Fundamental Thoughts of Aerodynamics. It's based on the book of Introduction to Flight 8th edition by Professor John D. Anderson. So enjoy. This video contains some foundation to enter aerodynamics world and talk with the same concept in mind later. To be a good engineer, we should speak with specific language which consists of some logical collection and assimilation of symbols, definitions, formulas, and concepts. This video will discuss about the language. Here the roadmap adapted from the book. First, we will talk about some physics that important to learn basic aerodynamics. We will start with some physical quantities of a flowing gas, which are first pressure, second density, third temperature, fourth flow velocity, and fifth streamline. We will talk with logic about the physical quantities. We will discuss about its symbol, definitions, formulas, and concepts regarding the 5 quantities. Then we will talk about source of aerodynamics force which related with the physical quantities. Also some discussion about equation of state, specific volume, and units that very important to learn aerodynamics. It is important to understand that the source of lift to make an airplane lifted is flow of air over the surface of airplane. Moreover, aerodynamics is the science to study the flow of air or any gas, and the aerodynamicist is the person who practices the science of aerodynamics. The study of the flow of gases is important in the design various flight vehicle and also to study of other flows as listed in the slides. Please read it carefully as it will become a big motivation to step further in learning aerodynamics. Here the 4 fundamental quantities in aerodynamics: pressure, density, temperature, and velocity, and let's enjoy in learning them. Please take a look to the illustration. The force exerted by the air per unit area to the hand is defined as pressure. The pressure exists basically because air molecule, oxygen and nitrogen molecules are striking the surface of the hand and transferring some of their momentum to the surface. And this is precise definition of pressure. Please read it slowly and carefully so you understand it well. The important thing regarding the definition of pressure is that although pressure is defined as force per unit area, we don't need to evaluate pressure only in a specified area. Usually the evaluation of pressure is point to point by using differential calculus. Next is the illustration for definition of pressure. Symbol for pressure is P. We have here the F as a force on one side of the A, and we use P equal limit dF over dA approaching 0 to define pressure. The equation for P in differential calculus form says that in reality it is a point property because we evaluate the force on a unit area that shrinks to 0, so it becomes a point. Unit of pressure are as follows: Newton per square meter, dynes per square centimeters, pounds per square foot, and atmosphere. We have finished discuss about pressure. Next, we will talk about density. The definition of density is as follows. The density of a substance, including a gas, is the mass of that substance per unit volume. The symbol for density is a Greek letter read as rho. Please read the example to understand what density is. Please read it carefully. See the illustration. We consider a volume of a gas and pick an infinitesimal cube containing point B. Although the definition of density is mass in a unit volume, we don't require an actual volume of 1 meter cubic or 1 cubic foot to evaluate it. Just like for pressure, we shrink the evaluation volume to 0 so that density is also a point property that could change point to point. Equation for density rho is as in the bottom part of the screen. It is using differential calculus. Unit of density are kilogram per cubic meter, slug per cubic feet, and gram per cubic centimeter. We are starting to discuss temperature. The symbol for temperature is capital letter of T. The temperature T of a gas is directly proportional to the average molecular kinetic energy. Definition of T is as appears in the bottom of the screen. The unit of temperature is Kelvin, degree Celsius, degree Rankine, and degree Fahrenheit. Now we will talk about flow velocity and streamlines. The symbol of velocity is v. The concept of velocity is similar with speed, but velocity should include direction of movement. Flow velocity along with pressure, density, and temperature is a point property. The speed and direction of the gas may vary from point to point in the flow because velocity is a point property. Here is another illustration about flow velocity. The velocity at any fixed point B in a flowing gas is a point property and can vary from point to point in the flow, so the velocity is a point property. If the flow is in a steady condition, the velocity does not fluctuate with time. In this condition, we can trace a fixed path a moving fluid elements go through. It's called a streamline as illustrated in this screen. If we can draw a streamline of the flow field, it is easy to visualize the motion of the gas. This is an actual photograph of streamline. This is streamlines over an airfoil model in a low subsonic wind tunnel. The streamlines are made visible by injection of filaments of smoke upstream of the model, then the smoke filaments follow the streamlines in the flow. This picture shows surface streamline. This is actual photograph of streamlines. It shows surface streamlines that made visible by coating the model with a mixture of white pigment in mineral oil. So the visualization of flow streamlines is a useful aid in the study of aerodynamics. Now we have finished the first block of roadmap. We have finished talking about physical quantities in aerodynamics. We start with the next block of roadmap, which is discussion about the source of all aerodynamics forces. Consider the illustration in the screen, which is the flow around a cone. From aerodynamics, we suppose to get its point properties of pressure, density, temperatures, and velocity, so we get the flow field. The function of theoretical and experimental aerodynamics is to calculate and measure flow fields of many types. Now we will talk about consequence of flow field. Its practical consequence is the object of flow field experience aerodynamics forces, and the source of aerodynamics forces are first pressure distribution on surface, and the second is shear stress or friction on the surface. Now we will discuss about the first source of aerodynamics forces, which is pressure distribution on surface. It always acts normal to the surface as described in the illustration around an airfoil. The net unbalance of the varying pressure distributions over the surface creates an aerodynamic force. Next, we will talk about the second source of aerodynamics forces, which is stress or friction on the surface. Different with pressure, shear stress acts tangentially on the surface as illustrated around an airfoil. The net unbalance of the surface shear stress distribution creates an aerodynamic force on the body. It is a fact that no matter how complex the flow field and no matter how complex the shape of the body, the only way nature has of communicating an aerodynamic force to a solid object or surface is through the pressure and shear stress distribution that exists on the surface. A primary function of theoretical and experimental aerodynamics is to predict and measure the aerodynamic force on a body, which implies in prediction and measurement of pressure and shear stress along a given surface, which needs the knowledge of the complete flow field around the body. Now we move to next box in roadmap, which is talking about equation of state for a perfect gas. Definition of a perfect gas is one in which intermolecular forces are negligible. In aerodynamics, we almost always deal with perfect gas in subsonic and supersonic flow. Equation of state for a perfect gas is P equal rho RT, with R is equal to 287 joule per kilogram Kelvin, which is equal to 1716 feet a pound per slug degree Rankine. We have reached to the new book of roadmap, which is discussion of units. Physical units are vital to the language of engineering. The end result of most engineering calculations or measurements is a number that represents some physical quantity, such as pressure, velocity, or force. For example, pressure is equal 100,000 Newton per square meter. Velocity is 300 meter per second. Force is 5 Newton. Newton, meter, and second are units. There are two main unit systems. The first is engineering units and the second one is SI units. Engineering students must be bilingual in units. They should understand engineering units to understand past literatures and fluently in SI units for their present and future works. SI unit system is a metric system based on the meter, kilogram, second, and Kelvin as a basic units of length, mass, time, and temperature respectively. SI unit is a coherent or consistent set of units. Please read carefully in this screen about example of this coherent set of units. The English engineering system of units is also a consistent set of units. The basic units of mass, length, time, and temperature are the slug, foot, second, and degree Rankine respectively. Please read carefully the application of these English engineering consistent system units to the second law of Newton. In the past, a non-consistent set of units frequently used by mechanical engineers that includes the pound force, pound mass, foot, and second. Please read carefully the equation of Newton's second law with this non-consistent system. There is a factor of Gc in this equation that different with consistent set of units F is I and engineering units previously. The screen gives illustration of comparison between slug in consistent units and pound mass in non-consistent units. Another non-consistent set of units that used in international engineering deals with the kilogram force, the kilogram mass, meter, and second. Please read carefully the example of application of these non-consistent units to the second law of Newton. We see that it involves the factor or coefficient of Gc. For everyday convenience, it is practical to use non-consistent system of units. But for technical world of engineering calculation, it is strongly recommended to use consistent set of units so that we will have F equal ma without factor of Gc. In aerodynamics, we use following convention set of units. We use consistent set of units which are the English engineering system units, which consist of pound, slug, feet, second, and degree Rankine, and also SI system units which consists of Newton, kilogram, meter, second, and Kelvin. The following table in the screen gives units involved in equation of state P equal rho RT. We will conclude the discussion about units into final points. The first one is, the units of a physical quantity can frequently be expressed in more than one combination by referring to Newton's second law as depicted in this screen. The second final point is, in the equation of state, T is always the absolute temperature where 0 degrees is the absolute lower temperature possible. Remember that T in equation P equal rho RT should be in absolute scale of Kelvin or degree Rankine. Now we reach the last block of roadmap. We talk about specific volume. Specific volume is frequently used in aerodynamics. Specific volume is the inverse of density. So the equation of state could be written as PV equal RT. The units of specific volume is cubic meter per kilogram and cubic feet per slab. And this is the end of this video about some fundamental thoughts of aerodynamics. Thank you.